All right, we are now recording, and we're in Chapter 3, Determinants. Okay, we're in Section 3.4, which is the last section in Chapter 3, Determinants, and 3.4 is Applications of Determinants. Now, this is a fairly long section. There are a lot of applications we're going to go over. I don't know if we're going to finish them all today. Oh, wait. Here comes Kira. Let me get her here. If I can get the pen to move. There she is. So we got doubled the class size now. We got the top and the bottom of the alphabet. We're just missing James in the middle. Okay. So Kira, I'm glad you're here. Any questions before we get started today? Okay, I saw your light come on, but I haven't heard anything. Were you trying to say something? Okay, good. Okay, I couldn't tell. Sometimes the sound checks out and sometimes it doesn't do well. Okay, like I was saying, we're in Chapter 3, Determinants, Section 3.4, Applications of Determinants, and we're on page 134, the first page of that section. This is a long section. There's a lot of applications we're going to be dealing with. They're quite different from one another, so it's going to take us a while to do this section. I am a little torn or how we're to approach this. I could publish for you. Okay, no, time out before we get that far. I'm guessing, but I'm not certain of this. Are both of you graduating this term, or are you going to be back in the spring? You are. How about it? Okay, if you pass this course, huh? Okay, okay. So I think if this is the only thing holding you up, you'll probably be okay. Now, the reason I asked that, the dean came out with pretty strong email saying, please try to get people to register for a spring term. My guess was that no one in this class, I don't believe James is going to be back in the spring either. Do either of you know that? I think he's graduating this term, but he may not be. So anyway, we'll find out if he shows up today. Hopefully he will. Um, so yes. As far as I know, yes. They have the last couple of terms, so I would guess it would do it again this term. Frankly, I can't see why. If it's virtual, I cannot see why unless you just want to have that as a souvenir or something. I don't know. Um, yeah, I wouldn't think so, but I don't know. They may be thinking, is this James coming in? I think it is. Let me see if I can get. Yes, I got him in. And perfect attendance today. Way to go, team. Okay. James, welcome. Glad you made it. We were just talking about you. I hope your ears are ringing. No, I'm just kidding. Are you graduating this term or are you going to be back in the spring? I thought you were. So all three of you are graduating, or at least Jesus is hoping we will be. Okay. So you won't be registering for classes in the spring, so I thought that was probably the case, but the dean was really on to us to encourage students to register for spring term. So, but y'all are all out of the picture then, which I congratulate you on doing. But if you know of people who will be back in the spring, encourage them to go on and get their registered for spring, because it's really making the administration panic because our enrollment is down right now. So please encourage people to. Now, why was I bringing that up? I can't think what my context was on that, but well, I've flown the coop now. Anyway, at the end of this term, and all three of you are in three of my classes, aren't you? Aren't all of you in Cal 3 and differential equations as well as this class? Please don't forget, and some of you have already turned them all in, your research papers. Please don't forget your getting all the tests in. Don't let them pile up on you at the end. Please try to get those things done. Okay, so let's talk about how things are going to end for this term. We've got, of course, today is, here's the other thing. I knew there was one more thing. We missed Thursday a week ago, I think it was, okay, because I had to have an infusion that day. And I think y'all had said you'd like to make up that class tomorrow. Is that still on? Are you interested in making up the class tomorrow? Yay or nay? Okay. Now, I think what y'all had said before was 8 o'clock tomorrow morning. Is that still good? I've got all morning that we could do it, but if you prefer to get it over with at 8, that's fine with me. Is that what you want to do? Okay. So 8's okay with everybody, or is that inconvenient for anybody? It's good for you, James. Is that what you said? Okay, and I believe Jesus was the one who suggested 8 in the first place. Is that right? Did you want to? Oh, okay. Meaning tomorrow. Is that every Friday or just tomorrow? Well, wait a minute. Weren't you the one saying you wanted it then? Okay. Okay. All right. Well, we'll try to have it done 8 to 9:15 tomorrow morning. We'll try to have the class. Okay. And if you can't be there, I'll still be recording it, and it'll be out there on YouTube videos if you do miss any of it. Okay. I'll try to be up here at 8 o'clock too. Toward the end of the week, I run out of gas pretty quickly, but I'll try to be up here by 8 and get it knocked out and over with. Okay. So it then probably will be the case that between today and tomorrow we'll probably finish section 3.4. So then what I'll do is go on and publish the test for chapter 3 tomorrow after that class. That's where I was sort of heading. I was going to say we probably won't get finished with it today, but I forgot we had the class tomorrow. At least we'll be far enough along you can do that. Okay, so that said, let's move on to these applications of determinants. Now the first of these, and we introduced this last time, is the adjoint of a matrix. Okay, we haven't gotten to what that is yet, but we were talking about the matrix of your cofactors. Okay, and this is not an easy concept. Okay, but if you remember, if you have a matrix, okay, and I don't want to write it all down, but let's picture this square matrix: A11, A12, A13, A14 up to A1n, A21, A22, A23. You got the idea. Down to AN1, A10, 2, AN3. You got a square matrix there. Now, what is a cofactor? Every one of those entries, like A11, its cofactor is what we call C11. Okay, that's what you get when you eliminate the first row, first column, and given the sign of that position, the 1, 1 position would be positive sign. Sorry, you would have the minor plus or minus the minor of that position. Okay, now you eliminated the first row, first column, and the minor of that, the positive minor of that, would be your cofactor. The next position would be the negative of the minor, and then the next one the positive of the minor. Okay, so you can come up with a new matrix here of your cofactors, and that's what they're going to mention here. Okay, that new matrix would be C11, C12, C13, dot, 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 up to C1N. I believe they're using the subscript N, aren't they? Yeah. And then you have C21, C22, C23, dot, 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 up to C2N. And then you have C31, C32, C33, doesn't draw threes well, dot, 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 up to C3N. And then you dot, dot, dot on down here to C sub N1, dot, 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 down to C sub N2, dot, 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 down to C sub N3, and then you dot, dot, dot everywhere across here, dot, 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 until you get to C sub N. Okay. Now, that's called the matrix of cofactors. Now remember, those cofactors are plus or minus the minors of the entry that you wiped out. Okay, that's what they are. Okay. Now, if you take that matrix of cofactors and then transpose it, that forms what we call the adjoint of a matrix. So the adjoint of that matrix A, and they don't have a real handy thing, so they just do ADJ of that original matrix A. And remember, this is so aggravating. Okay, of that matrix A would be the transpose of this. So that would be a C11 here, C12 there, C13 here, dot, 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 down to C1N here, C21 here, C22 here, C23 here, get carried away, dot, 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 down to C2N down here, C31, C32, C33, dot, 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 down to C3N, and then dot, 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 this all the way across to CN1, dot, 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 to CN2, dot, 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 to CN3, and then dot, 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 all the way across and down everywhere to CNN. That's not Cable News Network, by the way. Okay. That's the adjoint of A. So that's one application of determinants. Okay? Because to get these cofactors, you're doing the determinant. That is, the minor is your determinant. That's what makes these C entries here is a determinant. So, let's please clear that out of the way, okay? And let's do example 1. Find the adjoint of this matrix A. Here's matrix A. And this is a matrix. It's a 3 by 3 matrix. -1, 3, 1, 2. I'm sorry, I can't read. 0, -2, 1. And 1, 0, -2. Okay, that's the matrix A. Now, it says find the adjoint. Okay. Now, the adjoint of the matrix, you first do the matrix of cofactors. Okay, I'm going to do this. This doesn't have a special name. I think I'll call it C, okay, because all the entries are C. Okay, and this is going to be the matrix of the cofactors. Okay, how do we get that? We eliminate, say, this row and this column, okay, and then take the minor of what's left. That would be 4 minus 0, okay, and that is a positive position, so that's going to be 4, okay. I always like to check and make sure that I'm starting this right. Now, I hope my eraser mechanism continues working. Yes, it did. Okay, so I'm going to wipe out that column, wipe out the wipeout of that, and then do the second entry here. Okay, and do the minor for that. That would be a 0 minus 1, but that's a negative position, so that's going to be a plus 1. Okay, following it so far. Okay, this is the C matrix, the cofactor matrix. Okay, next, again, I hope this does continue to be kind to me. Let's wipe out this one. Now this is a positive position here, and you have 0 minus a minus 2, so that's going to be a 2. Okay, these are the the matrix of cofactors. Okay, next thing I'm going to do is wipe out, if I could just get the pen to cooperate, and it's not cooperating well. Okay, there we go. I'm going to this time, I think, well, I thought I had my eraser activated and it went off. There we go. Okay, I'm going to just sort of skip around here a little bit and do the 2, 3 entry here. Okay, now that's a plus, minus, plus, minus, and then when we do this, you get 0 minus a 3, but you had a minus position, so that made it a plus 3. So this one becomes a plus 3. That's the cofactor there. Okay, now this pen just goes wherever it wants to. Okay, now let's wipe out this one and go to this one. Alright, that's a plus position, and what's the cofactor here? That's a plus 2 minus 2, that's a 0. Okay, now let's wipe out. This is so tedious. Okay, now we're doing this position, which is a negative, and this will be a minus 6. That would be 6 minus 0, so that's a 6. Okay, that was easy enough to do. It just takes so long to get the thing to right. And what I'll do now, yuck! I wiped out my minus sign too, I believe. Let me make sure. Yep, that was a minus sign here. Okay, now we're doing this position, which is a positive position. That's 3 minus a minus 4. That would be a 7. Okay, now we'll wipe out. Come on, here we go. Okay, this is so slow to do this way. Okay, this is a plus, minus position here, and this would give us a positive 1, so that's just 1. Okay, and then finally the last one, which to get my pen to move. Okay, that would be this position here, which is a positive position, and that would be 2 minus 0. So that's just 2. So there is our matrix of cofactors. Okay, just the matrix of cofactors. Now we're ready to do the adjoint. It's the adjoint of the original matrix A, this matrix right here. And that adjoint is going to be the transpose of this one. So this will be a 4, 6, 7 going that way, a 1, 0, 1 going that way, and a 2, 3, 2 going that way. There's the adjoint of that matrix. Okay, 4, 6, 7, 1, 0, 1, 2, 3, 2. Now, you might ask yourself, okay, fine, what was the point of that? Okay, well, here's the point. The adjoint of a matrix can be useful for finding the inverse of A, and that's what this next theorem is going to say. Now, I would do this, type it in, but this is just going to be too difficult to type, so I'm going to do it this way. Okay? If I can get my pen down here, if A is an n by n invertible matrix. Okay, now number one, it has to be square. It has to be squared. It can't be invertible if it wasn't square. But it's not just squared, it is also invertible matrix. Okay, it's easier to do cursive than it is to print, but it's still not easy. Okay, then if it's invertible, it has an inverse. A inverse is equal to, now get this, 1 over the determinant of A times the adjoint of A. All right, now that's a definition. That's a theorem. It's true, okay? It works. The question is, why would you want to do that? Okay, because you remember, to get the inverse of A, all you have to do is join that to the identity matrix of the same size, and then do your own reductions. What we just had to do here was come up with the cofactor matrix and then transpose it. Surely that is more complicated than doing the other. So why in the world would you do this? Except it's doable. It's okay. Now, in the left-hand margin of this, there's a little remark here. Theorem 310 is not particularly efficient for finding the inverse of a matrix. The Gauss-Jordan elimination method discussed in section 2.3, much more efficient. However, it's theoretically useful, okay, because it provides a concise formula for the inverse of a matrix. Now, what does that mean? Okay, kind of what it means is you can program this pretty easily to do. You can program to do Gauss-Jordan elimination too. There's plenty of programs out there that'll do that. But this does give you a very specific concise way to find out that inverse. Okay, is it the most efficient? No, it isn't. Nowhere close. Okay, now if you think back to our very simplest matrices, like a 2 by 2, this is another remark on the left-hand column of that same page, Now let's see if we can do this. Here's a 2 by 2 matrix A. Okay, that was A, B, C, D. There was your matrix A. Now, what would be the adjoint of A? Okay, well, let's first do the cofactor matrix. Okay, cofactor matrix would be wipe out first row, first column, and that gives you D. Wipe out the first row, second column, and that would be minus C. Remember, that has a negative position there. Wipe out the second row, first column, and that gives you second row, first column, that gives you a minus B. Okay, because again, that's an odd position, a negative position there, and then wipe out the second row, second column, and that gives you A. Now, there's your the cofactor matrix. Your adjoint of A would then be the transpose of that, which would be D minus B minus C A. Okay, now that's the adjoint. And what the theorem just said, it's the inverse of that would be the determinant of A. What's the determinant of A? Determinant of A is A D minus CB, or BC, doesn't matter, and 1 over that, that would then be 1 over AD plus CB, or BC, whichever you want to say it. I'm sorry, that's a minus, not a plus. Okay. Well, the very thing I wanted to keep, I erased, and the thing I wanted to erase, I kept. Okay, that's the 1 over that, and then this would be the adjoint, which would be D minus B minus C A. Now, if you think back how we did that when we did do a 2 by 2 matrix, what we did was 1 over the determinant. That's where we first ran into a determinant, and then we did exchange the 2 diagonal entries and negate the off diagonal entries, and that's exactly what we've got here. So that's it, gave us exactly our 2 by 2 formula that we came up with earlier. Okay, now let's go on to example 2. All right, for me to erase what we've got here. Any questions before we do it? Okay, so here's example 2. It says use the adjoint of A to find the inverse of A. Now, here is your matrix A. I wish I sort of had left what I had up there. A was negative 1, 3, 2, 0, 2, 0, negative 2, 1, 1, 0, negative 2. Okay, now if you look across the page, you'll see this is exactly your matrix A from example 1. Okay, and we've already done that. So we know that the adjoint of A, okay, we did that on the last one, the adjoint of A was this matrix here, 4, 6, 7, 1, 0, 1, 2, 3, 2. We just did it, and I erased it. Sorry that I erased it. Okay, now what does it tell you? The theorem 310 tell you was the inverse of A inverse was 1 over the determinant of A times the adjoint of A. Now, we've already got the adjoint of A, so that's not going to be an issue. We need to do the determinant of A. So let's do it down here. Okay? Okay. Now this isn't quite accurate, but you get the general idea. Minus 1, 3, 2, minus 1, 3. You don't usually have a determinant of a rectangular matrix, but you know what I'm doing here. 0, negative 2, 1, 0, negative 2, and 1, 0, negative 2, 1, 0. Okay, and let's do that. Your down diagonal here is going to be a minus 4. Down diagonal here is going to be a plus 3. Down diagonal here is going to be a 0. Okay, up diagonal here is going to be a plus 4. Up diagonal here is going to be a 0, and up diagonal there is going to be a 0. So what do you have? The determinant of A is equal to 3. Okay, so this would be 1/3 the adjoint of A, and we just wrote that down a little bit ago. 4, 6, 7, 1, 0, 1, 2, 3, 2. Okay. Now, if you multiplied those through, you don't have to. I find it easier just to leave them like that. But this would be a 4/3 to 7/3, 1/3, 0, 1/3, the one didn't show up there, did it? Okay. And 2/3, 1, 2/3. Okay. You didn't have to do that, but you could. I've got to stop just for a moment here because I'm losing my voice. Sorry about that. I think I'm going to need to open the second one because okay, sorry. Let's see how they did it. And they got a 4/3 to 7/3. I said, I can't believe I wrote that. Nobody corrected me at 7/3. I don't know how it got to be a 7/7. Okay, 1/3, 0, 1/3, 2/3, 1, 2/3. Got it. Okay, now, how do you verify that is indeed the inverse? Well, you could take matrix A and multiply by, now here's what I would do, folks. I would multiply by this one by that one, just to keep from having all those fractions in there. So let's see what happens if we do this. I don't know where to begin. I think I'm going to begin by erasing a lot of this, okay? I want to keep the things that are important here. We don't need the adjoint anymore. We're through with that. Okay, we don't need this form here anymore. We're through with that. I am going to keep that, so I will wipe out this one too. Okay, that gives me room enough to work. Now again, what I'm going to do is just multiply this one by that one, and then at the end take a third of it. So I think you'll see it works out pretty nicely that way. So it'll be a -1, 3, 2, 0, -2, 1, 1, 0, -2 times 4, 6, 7, 1, 0, 1, 2, 3, 2. Okay, and this is going to produce a 3 by 3 . All right, let's do first row, first column. -4 plus 3 would be a -1, plus 4 would be a 3. I hope, yeah. Okay, first row, second column, be a -6 plus 0 plus 6. That's going to be a 0. Good so far. First column, second row, I'm sorry, first row, third column. I'm about to lose it all, folks. Let me get a little more caffeine here. By Thursday, I am running out of gas, especially this time on Thursday when I'm normally trying to consume a little bit of food. I'm not. Okay. First row, third column. That's a -7 plus 3. That would be a -4 plus 4. That's a 0. Okay. Second row, first column, a 0 -2 plus 2. That's a 0. Second row, second column, that would be a 0, 0, 3. Perfect. Second row, third column, a 0 -2 plus 2. That's a 0. Third row, first column, 4 plus 0 is 4, minus 4 is 0. Third row, second column, that would be a 6, 0, -6. That's a 0. And then third row, third column, 7 plus 0, -4. That would be a 3. And then just take a third of that and you get 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, so sure enough, that gave us exactly the inverse of A. All right. So that's one application of determinants. You can use those to come up with a inverse of a matrix. Not easy, okay, not simple, but it's doable. Okay. The second of these is going to be called Cramer's rule. And for those who haven't already done a research paper here, here's another potential topic. Who in the world is Cramer? Well, Gabriel Cramer It gives us lifespan here, 1704 to 1752, which was back at the time when we were still colonies. In fact, of course, Alabama wasn't even in existence at the time. But in a way, Cramer's rule uses the determinants to solve a system of linear equations in variables. The rule applies only to systems with unique solutions. If you don't have a unique solution, you can't solve it, obviously. Okay, so here's what we're going to do with Cramer's rule. Okay, we're going to start off with a simple 2x2 solution, a 2x2 equation, system of equations, and that's going to be this: A11 times x1 plus A11 12 times x2 is equal to B1. Okay, A21 times x1 plus A22 times x2 is equal to B2. Okay. Excuse me just a moment again. I'm so sorry. It seemed like I had been getting a little stronger every day as far as the anemia went. I felt like I was anyway, but today I feel like I'm going downhill really badly. I don't know why. All right. Now, how did we go about solving a system of two equations, two unknowns? This goes way back to some algebra course in the long distant past. Okay. Well, one way was elimination by addition. Okay. So let's just say that what we're going to do is multiply one of these equations by one thing, another by something else, so we can eliminate one of the variables. Okay, now I'm going to try to do this in the way that the book is doing it. If we wanted to eliminate x2, say, then we're going to multiply one of these equations, let's say the top one, by A22. I believe that's right. A22, and multiply the bottom equation by minus A12. Okay? Now, it's so much easier when you have numbers here rather than letters with subscripts. They get really messy. But let's do what we just said. So the top equation would be A11 A22 times x sub 1 plus oh man, this thing is such a pain in the neck, plus A12 A22 x sub 2 equal to A22 B1. Okay, now let's multiply the second equation by negative A12. So that would be negative A12 A21 x sub 1. This is such a pain. Okay, minus A12 A22 x sub 2 equal to minus A12 B2. Now, what you see happening here, these two are identical. They add to 0, except the opposite signs. So what do we have now? A11, A22, X1 minus A12, A21, X sub 2. No, I'm sorry. These are both times X sub 1. I'm going to put these in parentheses here to keep me from having to write as much. Okay, A11, A22 times X1 minus A21, 12, A21, X of 1. So just do them like that. And this is equal to, goodness, I got to sneeze, sorry about that. A22 B1 minus A12 B2. Okay. I think this may be James coming back in. He had to bump out for a moment. Let me see if I can get him back in. Come on, James. Show up. Let me see if this will work. I think it did. Yeah, he's back, or he's coming back. Okay. I saw you had to bump out. I'm glad you got back. Now, what does that give you? X sub 1 is equal to A22 B1 minus A12 B2 over A11 A22 minus A21 A12. That's our answer for X1. Boy, a lot of work to do. If we had just numbers there, it'd be so much easier to do. But that's the very generic case of it. Now, if you did the same thing and eliminated X sub 1, say by multiplying the top equation by A21 and the bottom equation by minus A11, or reverse, then you would have come up with this. X sub 2 is equal to I have to stop and think a moment on it. I think it's A11. Yeah. A11 B1 minus A21, I believe it is, B2 over A11 A22 minus A21 I can't read my writing there, A12. Okay, let me make sure I got that one right. I got it backward. Okay. This is the 2 here, and this is the 1 here. Yeah, sorry. Got those backwards. Now, so what, okay? We could do that, but that's sort of messy. Well, let's take a look and see what we've got here, though. Notice your denominators are the same in both cases. And not only are they the same, those denominators are your determinant of A11, A12, A21, A22. Because do the determinant. A11, A22 minus A21, A12. And both of them are exactly the same. So there's your determinant. Okay? That's the denominator of the determinant. Well, the determinant that's in your denominator. Okay, I'll get it right one of these days. Okay, what happens about that extra 1 though? Okay, well, notice what it is. Okay, since we made that into a determinant, this one would be the determinant of B1, B2, writing it that way, A12, A22. Okay, because look at that. A21, B1 minus A12, B2. A22, B1 minus A12, B2. Okay, that's your x sub 1. And if you did the same thing for x sub 2, that would be your denominator is the same, A11, A12, A21, A22. That's the determinant of those coefficients there. And your numerator here would be the determinant of A11, A21, B1, B2. Sorry about that. Okay. Now, what does that produce here? Okay. Your denominator is the determinant of your coefficient matrix. That's it, every time. Okay. Your numerator, if you're doing x1, replace the coefficients for x1 with your constants, b1, b2, but keep these coefficients there, and there you have that determinant. If you're solving for x2, keep the coefficients for x1, a11, a21, and somebody let me get away. Oh, no, yeah, there it is. I got it right. Okay. Keep that one, but then do your b1, b2 in for your coefficients of this term, and the denominator is the same. That's Kramer's rule. Okay. Now, is that any easier than Gauss-Jordan elimination? Probably not. Okay, probably not. However, notice you only take that denominator once and use it for both ones. Okay, the numerator, take that determinant once for each of those, and as long as they're pretty small, it's not too bad. Not too bad to do. So let's do with numbers. I'm sick and tired of doing these only with letters. Okay, so let's clear that and let's do example 3. 4x1 minus 2x2 is equal to 10. 3x1 minus 5x2 is equal to 11. Two equations, two unknowns. Okay. Now, if you wanted to eliminate the way we did, it's sort of a pain in the neck because you have to multiply the top equation, say, by 5 and the bottom equation by -2 or something like that, and it gets to be some pretty big numbers. But let's just do it Kramer's rule. X sub 1. The denominator is going to be the determinant of your coefficient matrix. 4, 1. I'm sorry, where did that come from? All right, 4, 2, 3, -5. That's a -2. I don't know why I can't. Okay, that's your denominator. What's your numerator? Well, rather than the coefficients of x1, you put the constants. That's going to be 10, 11, and then these are going to be the -2, -5. Same for that. Your x sub 2, your denominator is going to be just like it was before, 4, -2, 3, -5, and your numerator is going to be 4, 3, I hate doing that, 4, 3, 10, 11. Okay, now what is this one? Yeah, they're big numbers, but they're not bad. That's going to be a -50 plus 22 over -20 plus 6. Okay, x sub 2 is going to be 44 minus 30 over -14. I don't have to do that again. I just need to do it once. So x sub 1 is equal to, looks like about a 28, -28 over a -14, which is a 2. Okay, and x sub 2 is a 14 over a -14, which is a -1. Okay, let's see if that indeed works. Okay, this would be a 2 here. 4 times 2 is 8, plus 2 times 1 is 10, is 2. That gives you 10. That works. And this one would be 3 times 2 is 6, plus 5 is 11. Yep, there it is. Okay, without very difficult mathematics at all. And here is James coming back in. Evidently, either James is having problems staying in or is having to go in and out with his work or whatever. Okay. All right. I think he has his microphone on too. So there's using Kramer's rule, example 3. Okay. Now, that was a simple 2 by 2. Wouldn't have been hard to do it otherwise, but it was pretty easy with Kramer's rule. Okay, now with that in mind, Kramer's rule generalizes to systems of linear equations in n variables. The value of each variable is the quotient of 2 determinants. The denominator is the determinant of the coefficient matrix, just like we said before. The numerator is the determinant of the matrix formed by replacing the column corresponding to the variable being solved with the column representing the constants. Okay, now that's a lot of blah blah blah. Okay, but it's a pretty simple blah 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 if you're doing that. So let's say that we have this thing. Now again, all these subscripts and stuff, it drives me sort of crazy. A11 x sub 1 plus A12 x sub 2 plus A13 x sub 3 is equal to B1. Okay, A21 x sub 1 plus A22 x sub 2 plus A13 x sub 3 is equal to B2. A31 x sub 1 plus A32 x sub 2 plus A33 x sub 3 equal B3. Alright, excuse me just a minute, I am just about to lose it. I need to eat something fairly soon. Okay, so here is your solution. I mean, basically you can write it down. X sub 1 is equal to, your denominator is that coefficient matrix, A11, A12, A13, the determinant of that. A21, A22, A23, A31, A32, A33. Okay. Now, your numerator here will be B1, B2, B3, A12, A22, A23. Nope, I said them backwards. 3, 3, right, 3, 2. Okay, hope that was someone catching my error. This is A13, A23, A33. Okay, now X sub 2 is simply that determinant, I'm just going to leave it the determinant of A, because that is what it is. It's the same. You only have to calculate it once. Okay, your numerator determinant is going to be A11, B1, A13. Okay, A21, B2, A23, A31, B3, A23, 3, goodness gracious, why can't I say that right? Okay, that's what that one is. The X sub 3, same denominator, your numerator is going to be A11, A12, B1, A21, yuck, A22, B2, and A31, A33, B3. Okay, that's hard to read, but that's what it is. Over that determinant of A. Alright, that's the top of page 137. Okay, now they have names for this. As I said, that the bottom determinant is always going to be the determinant of A. The top one here will be determinant of A1. That's where you put the B1s instead of the X, or the first group here. They call this A2, which you put the B2s in the middle coefficients, and this one they call A3, where they put the B's in the third column. Okay, and they don't spell all those out, but that's what they get. Okay, and that's theorem 311, which if you have n linear equations and n variables, the coefficient matrix A with non-zero determinant then this is your answer. x1 is the determinant of a1 over the determinant of a. x2 is the determinant of a2 over the determinant of a, and x3 is the determinant of a3 over the determinant of a. Okay, now there's one more example here of Cramer's rule. Let's see if we can do it. Don't know if we're going to have time or not, but let's give it a shot. Okay, and you can go to LarsonLinearAlgebra.com for an interactive version of this type of an example. Okay, and this stinking thing. Okay, here's your system of equations. Minus x plus 2y minus 3z is equal to 1. 2x plus z is equal to 0. 3x minus 4y plus 4z is equal to 2. Okay. It says use Cramer's rule to solve that system of n linear equations for x. They only ask for the x. The y and z won't be hard to get either. But let's do the x first. Okay. So x is equal to, now let's do the coefficient matrix first. Minus 1, 2, minus 3, and I'm going to just repeat minus 1, 2. Okay, 2, 0, 1, 2, 0. 3 minus 4, 4, 3 minus 4. Okay, now let's just do our diagonals there, and that would be a 0 here, that would be a 6 here, and this would be a plus 24. Okay, let's do our up diagonals. That's going to be a 0. Now if I could read my writing here, that's going to be a plus 4, no, a minus 4, because it's an up diagonal. Okay, and this will be a minus 16. Okay, so this will be a 30 minus 20 equal 10. Okay, let me see if I got, and why that quit drawing, I don't know. Okay, this is such a pain in the neck. I'm trying to draw an equal sign and it just won't draw. Okay, your coefficient matrix is a 10. Got it. Okay, determinant is a 10. So this is going to be, the x value is going to be something over 10. Well, what is the something? The x sub 1, I'm going to phrase it that way, is going to be the determinant of 1, 0, 2. You put in that there, and then the others are going to be the same. 2, 0, minus 4, and the next one's going to be a negative 3, 1, 4, and then repeat the first two, 1, 0, 2, and actually this one I think will be easier just to do the determinant as it is. Okay, let's just use this row and that column. Okay, first that's going to be a minus 1, because plus, minus, plus, minus. So that's going to be a minus 1 times the determinant of what's left. Minus 4 plus 4. No, minus 4 is minus 8. So this is going to be an 8. So your numerator is 8. Denominator is 10. That's 4 over 5. Okay. Now, that's all they asked for was the 8. So it was the x value. It's not hard to do the y and the z. Do you want to do those next time? That would be tomorrow morning. Or do you want to just do those on your own? Want to just do those tomorrow morning? Okay. Let me erase here. Now, we didn't get as far as I had hoped today, or we seldom do, but we'll pick up and do the rest of example 4, even though they don't ask for it, tomorrow. That will be on 137. Then we'll do the area, volume, and equations of lines and planes. That will be on 138, 139, 140, 141, and get there. So homework exercises 3.4. Do any of the odds 1 through 7. They're all at Calc Chat. Any of the odds 9 through 21. They're all at Calc Chat. Any of the odds 23 or 25. They should be at Calc Chat. 27 should be at Calc Chat. And we'll hold off there and pick up the rest of those next time. All right. Any questions? Okay, good deal. We'll see you in the morning, hopefully bright and early, 8 o'clock. Knock out that class that we missed, and we'll be on. And then hopefully later in the day I'll get the test, the chapter 3 test, posted for you so you can work on that this weekend. Any questions? All right. Well, then take care. I'm going to stop sharing now, and we'll end the meeting for all of us. Any last thoughts, parting shots? Look, folks, be safe, be careful. It looks like a beautiful weekend. Don't let your guard down. The virus is still there in force. The numbers, the counts are rising like crazy. Be careful, people. Okay? We'll hope to see you on Monday, all 3 of you on Monday, right? So take care. We'll see you then. Bye-bye.